When I was an undergraduate student, I had never heard of biostatistics, much less thought about it as a career. I had taken one statistics course. It was required for my math major. And I don't know about you, I found it a little dull, stale. And as a matter of fact, I noticed on the way in here, students were asked on a big whiteboard, they were asked, what are some impossibilities? And among the other things, I saw a statistics course was written out there as an impossibility. I feel your pain. When I took statistics, I didn't think it was connected to the real world. I didn't think it was connected to people, and I didn't see that it was connected to my life in particular. Calculating the lifespan for a light bulb, the average lifespan for a light bulb for a company, that was not for me. Or thinking about the itinerary, the most efficient itinerary for a trucking company to get from one place to another, I wasn't interested. I wanted more. I wanted to improve human health. I wanted to be in public health. And I wanted to do it through this math degree. So imagine my intrigue when I began to learn that some of the concepts in statistics that I thought were settled were actually misused, actually were misinterpreted very much of the time. So what I'm going to talk about today is an intriguing, I think, intriguing topic in biostatistics, the intrigue of p-values. Now, it will surprise nobody in here that I am not a big fan of controversy or drama. I have never seen a single episode of Real Housewives, Survivor, or The Kardashians. But give me a good scientific catfight, and you got my attention. So I'm talking about the intrigue of p-values. That's going to be the related subject of statistical significance. It's an open, messy secret in science. I think of it as the Jerry Springer show of biostatistics. I'm going to start out with defining it, sharing the framework that many people are taught, and then talk about how pervasive it is, how it's problematic. So a p-value in scientific research is we begin with some kind of statement called the null hypothesis. Just think of it as a statement of no difference. A typical one might be no difference would be new drug and old drug, they have that same effect. And then we compute, assuming that there's no difference, assuming this null hypothesis, we compute the probability of getting our data or something more extreme. And then if our p-value is small, students are taught that they can reject this null hypothesis, and they're taught that they can label it as statistically significant. On the other hand, let's say that we assume that there's no difference. I collect my data. I get something that's really not so unusual. I get a p-value bigger than this arbitrary threshold. Then students are taught that they can fail to reject that statement of no difference. It's taught that it's not statistically significant. Now, as a human, we like this. It's very clean and neat. It helps us to make a decision. Unfortunately, many people want to overstate this framework, use it in ways that it shouldn't be. My first claim is that these p-values are pervasive. Why should you even care? Maybe you don't run across these p-values in your everyday reading, etc. I believe that they are impacting many things that we are reading in the science field. They're pervasive. They're everywhere. They're behind lots of the scientific discoveries that you're reading about and that you're interested in. During the week that I was preparing this lecture, I went to Google and I Googled New York Times Health News just to see what the top topic was. It happened to be, in this week, study links high fluoride exposure to lower IQ in children. Might have been autism and vaccines, you name it, scientific, public health issue, etc. Now, I was one click away from this, which was the research that this came from. And you'll notice in this research that it is this column of p-values, not just one or two, lots of p-values. And we know from that framework that many scientists, many researchers, many data consumers are going to be looking at this p-value column, and they're going to be looking at small values and thinking statistically significant, and maybe they're thinking therefore important. They may be looking here for big p-values and think that they failed to find a difference. Maybe that difference is just not important. So this is a cornerstone of scientific reasoning. If you scratch the surface on many of the things that you are reading in science, health, etc., it's relying on these p-values. So to bring this point home, there were some studies done about how many p-values are in research. And in my discipline, public health, it's estimated about 72% of journal articles in public health have these p-values. And they don't just have a few. For example, in the medical literature, an article did the math. On average, there's about 36 p-values per article in these major medical journals. So far, everything is fine. It's used a lot. I hope I've made the case that it's used a lot. But p-values themselves are problematic because people take them to mean more than they were ever intended to mean. Let's talk about some of the misinterpretations, and there's lots. I'll just mention a few of the misinterpretations of p-values. Over here, whenever a p-value is small, some people take that to mean there is a misinterpretation that they have found an important difference. This is a mistake. This is a misinterpretation. What could be happening is perhaps this is just a large sample size, but not a clinically important difference. On the other hand, let's say that you do your study, you assume the null hypothesis, you assume no difference, you get something that is reasonably common, a big p-value, then students sometimes interpret this as meaning that the difference that they found is not important. They may interpret it to mean that they found evidence of no difference. These are mistakes. These are common mistakes, and there's lots more. The reason this one is wrong is this could be driven by a sample size that's too small to detect even an important difference. So the sample size is wrapped up with the effect size, how big. And it's very easy to make these misinterpretations, even for people who are really bright. Bright, educated, etc. So a little hard to read, and that's okay. Who misinterprets p-values? In my experience, lots of people. Lots of really bright, smart, well-meaning people. So here's an article that asked medical residents to interpret a non-significant p-value, and sort of smushed up there in the right-hand corner is a statistic which is they answered correctly 60% of the time, and 40% of the time they misinterpreted p-values, a non-significant p-value. So some of our most well-educated people who should know these things. Who else misinterprets p-values, and how often do they do it? Well, people like me, epidemiologists, researchers, statisticians, can sometimes fall prey to these misinterpretations. Here was a study, and they asked two questions. One was interpreting a p-value that was significant. One was a p-value that was not significant. They asked doctoral students and statisticians and epidemiologists to interpret them, and 10% of doctoral students answered both questions correctly. 13% of statisticians and epidemiologists answered it correctly. So I'm making the case that even people who do this for a living can misinterpret p-values, and it can have a devastating effect to how we understand the data. In my experience, who misinterprets p-values? Lots of people, lots of the time. So let's look at an example. This is an example of a study that was looking at the relationship between active smoking and COVID. Something all interested, I hope. And in the text up there, you'll see that they looked at that association and they found a non-significant p-value. You'll see that p is equal to 0.254. And then in the text, they characterize that as no significant association. A correct interpretation is that they failed to find an association. Unfortunately, though, when they titled the journal article, they titled it incorrectly as "Active Smoking is not associated with the severity of smoking." We can't make that conclusion, okay? The lack of significance could be due to a small sample size. So this is an example of a common misinterpretation where they're equating failing to find an association with finding evidence of no association. What can we do about this? Well, we have several tools in our toolbox. One is what we're doing right here, awareness, so that we all know to be careful of these p-values. When we see those attention-grabbing headlines, the health news, they can be often built on a framework of p-values which are problematic. They are easily to be misunderstood. P-values were never intended to be decision rules. Okay, they were never meant to be up or down, right? They were meant to be used in another way, and we have hijacked the way that we use them. So awareness is one way to address this. Another way to address this is education, and we made great strides. Lots of researchers, lots of people in scientific fields are taking more coursework that involves statistics and research methods, and we know this. The literature out there is strong for this. Another thing that I'll suggest as a possible solution, or a promising solution, is to, instead of using p-values, is to use confidence intervals. So the framework for p-values we have seen can be misleading. It's a little slippery, right? Confidence intervals approach the question in a different way. It's a framework that often captures the value that we are after in the population. And that's better anyway. Wouldn't we like to know an interval that has that value in the population rather than p-values, which what they're trying to do with the p-value is to eliminate a particular value such as no difference. So in conclusion, I'd like to encourage you when you are reading those headlines about scientific discoveries to realize that behind that is research that's often based on p-values, and those p-values can be problematic. I also want to share with you to be aware of this. The next generation is being educated about this. And we want people to use alternatives to p-values. And when they're used, we want them to be used correctly and cautiously.